So now that we have finished our review of a single action potential, let's take a look at how action potentials move across the length of a neuron. So to start, we need to quickly revisit neural anatomy. So let's take a look at that. In this drawing of a typical neuron, I'm coloring in where the action potentials happen. So they can happen in the axon hillock, the axon, and then the axon terminals, almost all the way down to the end. Action potentials move across the length of the axon in a single direction, from the axon hillock towards the axon terminals, and this is always the case. In fact, because action potentials usually start at the axon hillock is sometimes referred to as the trigger zone, in that it will trigger a wave of action potentials down the length of the axon and to the axon terminals. So action potentials are going to start in the axon hillock and then propagate down the length of the axon. Now, it's not just one action potential, it's multiple action potentials. And the way this works is not terribly unlike a set of dominoes. When you have one domino and you push it over, every other domino that's in the row will start to fall. And so it turns out that action potentials propagate action potentials. So one action potential is like a domino leaning on another one that then pushes that domino over, etc. So you get a series of action potentials going down the length of the axon all the way down to the axon terminal. And it's absolutely critical that the flow of action potentials is in that direction and doesn't backflow. So let's ask ourselves, how do action potentials beget action potentials? In other words, how does one action potential cause the neighboring section of membrane to also have an action potential? And for that, we have to go back to our sequence of events in an action potential and remember that an action potential starts when a sodium gate opens in response to a -55 threshold. In the previous lecture, I said, we don't know how that -55 threshold arises, but we do know that it does, and when it does, that sodium gate will open, and then an action potential will proceed to occur. And once you reach that -55 threshold and the sodium gates open, everything you see here is kind of on autopilot, meaning it happens the same way every time. There's no changing the tracing, deciding halfway through that you're going to quit. It's going to go. So the critical piece then is reaching that -55 threshold. Well, what causes that initial depolarization? And it turns out it's probably some sort of depolarization that's happening in the membrane next door. Let's take a closer look. So in this drawing, I've actually blown up a section of the axon, and I have sodium ions in red outside of the cell. I'm going to take the yellow swath of plasma membrane and assume that I'm going to have an action potential happen in that yellow swath, not the green section, just the yellow section. We know that the first step of an action potential is going to be that voltage-sensitive sodium gates open, allowing a mass influx of sodium into the cell. Well, that sodium doesn't just stay there. It starts moving about. It starts dispersing. And so some of the sodium moves left and some of the sodium moves right. When the sodium starts moving left or right, that actually brings positive charge to the neighboring membrane. And so it turns out that this positive charge is what creates the depolarization needed to start an action potential in the adjacent section of membrane. So as that positive sodium leaks over to the green membrane, the voltage-sensitive sodium gates nearest to the yellow membrane are going to open. And so I've colored those areas in red. Those are going to represent voltage-sensitive sodium gates that are opening, allowing more sodium into the cell. And so this is going to not only depolarize the adjacent membranes to the red areas, but also start action potentials in those red areas. So now the action potentials that occurred in the yellow areas are going to trigger action potentials in the red areas. And the cycle is going to continue. depolarization at the red areas is going to diffuse over to the green areas and the yellow areas and cause depolarization in those membranes too. So this image here demonstrates kind of what I showed. It starts with a region of the axon that they've highlighted in yellow. Now notice that they have the positive charge coming in, but they actually put negative charges on the outside, whereas all of the membrane that is not doing an action potential, it's at rest, or potentially it's recovering from an action potential, it is showing the negative sign inside. And that's just a really simple way for textbook publishers to denote that the membrane potential is negative. That is, the cell has more negative charge than the outside. But remember that during an action potential, we crest at plus 30. So when we crest at the plus 30 mark, the inside of the cell is actually more positive. And so you can denote in a very simplified way that an action potential is in the process of occurring, that you're kind of in the middle of it, with showing the positive charge on the inside and the negative charge on the outside. So what this is showing is that when you get positive charge coming in, we expect it to move both directions, which I described. Now, if there is no refractory period, and we'll talk about that in a moment, but if there is no refractory period, then that should trigger an action potential over here and an action potential over here. That can't happen. Otherwise, this entire exercise would be meaningless. You would simply have a never-ending cycle of action potentials, constantly propagating action potentials in a never-ending positive feedback loop. And so, again, we can't have that happen, but suffice it to say that the part of the membrane that just finished an action potential does not see, hear, experience that positive charge. It does not respond to it. So therefore, there is no backward flow of action potentials. The only parts of the membrane that are responsive are going to be parts further downstream the axon. In other words, farther away from the cell body. And so in this way, even though positive charge comes into the cell and diffuses both directions, only one direction responds. The other direction does not do anything. And so this allows for the action potentials to continue to propagate in one direction. So I mentioned there are two types of refractory periods. They are called absolute refractory periods and relative refractory periods. It is the absolute refractory period that ensures that the flow of action potentials is one way. Now, the term absolute refractory period refers to a period of time during and or after an action potential where that section of membrane is completely non-responsive, meaning it doesn't matter how much depolarization you throw at it, how much you poke and prod at it, whatever you do with it, it simply will not do an action potential. So in this drawing here, this region is in the refractory period. In other words, you can see here that even though positive charge is coming over and potentially bringing that membrane potential back up, it's not doing anything. It's not going to respond. The sodium gates are not going to open. There's not going to be any action potential. So the purpose or the importance of that absolute refractory period is to ensure that one-way flow of action potentials down the length of the axon. So make sure you pause the video and copy this down in your notes. And then I'm going to reiterate that again, if we didn't have absolute refractory periods, we would end up with this never-ending loop going backwards and forwards of action potentials, causing action potentials, etc. And there would be no point to any of this. The entire point of the action potentials is to ensure that electricity was going one way. I mean, imagine for a moment if you had an electrical cord where when you plugged it into the outlet and then you had your light on the other side, electricity sometimes went to the light, but then sometimes it went from the light back to the grid and then back again, and your light was like, I don't know. You'd be like, no, I want electricity just to go to the light. So in the same way, you want electricity to just go down the length of the axon towards the axon terminals. That is what we mean by the flow of electricity going down the length of the neuron. So now let's talk about the mechanics. Why does the absolute refractory period exist? I mean, we know the value of the absolute refractory, but what are the mechanics? What's actually preventing a section of membrane from engaging in a subsequent action potential? And the answer has to do with the sodium gate. So remember in the prior lecture, I talked about the positioning of the gates during the sequence of the action potential. We started with one gate open, so it went something like this. Then the bottom gate dropped, and then the top gate closed, and then we spend another 1.5 milliseconds resetting. You can almost think of that as like winding it back up. During that reset period, the sodium gate will not respond to any voltage change. So from the time the bottom gate opens to the time that the sodium gate has completely reset is about 2 milliseconds. And so 2 milliseconds represents the absolute refractory period. The reason why the absolute refractory period mechanically exists is because the sodium gate is completely unable to respond to any subsequent voltage change until it's reached its reset configuration. All right, so go ahead and write this down. And then I wanted to draw your attention over here to this idea of the absolute refractory period and this idea of excitability. The excitability is kind of a weird descriptor that describes how likely some section of membrane is to engage in an action potential. So what starts the action potential? When the membrane potential reaches minus 55 millivolts, right? And the baseline, if nothing is happening, is going to be minus 70. So that's a plus 15 millivolt difference. Okay, so in other words, the membrane potential has to climb plus 15 to start an action potential. How easy is that? It's actually pretty easy. So if a membrane potential is already pretty close to threshold, we say that that has high excitability. It's like ready to go. Just you got to poke at it and it's like, oh, okay, we're ready to go. We're ready to have an action potential. It just needs to get that plus 15 bump up to the minus 55. It's ready to go. Okay. During the absolute refractory period, the excitability is a big donut hole, 0. Why is it 0? Because it doesn't matter what you do with the membrane potential. You simply cannot prod another action potential to happen in that section of membrane. So we can see here that the excitability is high when the resting membrane potential is at minus 70. As it climbs, we reach that threshold. And once we start an action potential, the excitability drops to 0. Again, the excitability is a measurement of how easy it will be to start a subsequent action potential. And here it's 0 because you're in the middle of one. And as we continue all the way down here, you can see it's 0, 0, 0, 0, 0. And then this is where the sodium gates reset. Okay, now an action potential is possible. It is possible, but it's harder to start. Why? Because we have a bigger hill to climb here. When we started our story, we were at minus 70. And so in order to get to minus 55, we needed a plus 15. In other words, we needed enough depolarization that we just brought us at plus 15. But here at the 2 millisecond mark, we're hyperpolarized. It's a harder climb. It's farther to go. So we need more positive charge to bring that membrane potential right back up here to start a subsequent action potential. And so from our excitability gauge, we are excitable, but not very excitable at that 2 millisecond mark. As our membrane potential continues to get closer and closer and closer to minus 70, it's a little easier and easier and easier to make that jump to the minus 55. So our excitability continues back up. By about the 4 millisecond mark, the membrane potential has returned to the minus 70 baseline. And at that point, you are as excitable as you're going to be. So the period between 2 and 4 milliseconds is referred to as the relative refractory period. And the relative refractory period is a period in time in which you could start another action potential, but it's harder to do. Now, why is it harder to do? Once again, the membrane potential is hyperpolarized. Remember, to start an action potential, you have to get to minus 55. So if you're here at minus 70, that's not a hard jump. But if you're way down here, you got to get a lot more positive charge to get up to that minus 55 threshold. So we call that period relative refractory period. Yes, you can do an action potential, but it's harder to trigger. Now, what is the value of a relative refractory period? Well, that's something I'm going to put a pin in because we're going to address it actually multiple lectures later when we get into coding stimuli intensity. So we'll come back to what the value of that is. But for now, do understand the mechanics. The mechanics are because it's just you have to have more positive charge to get from a hyperpolarized state back up to minus 55 millivolts to start the next one. All right, that concludes our lecture on action potential propagation and refractory periods. I'll see you for the next one on speed of propagation and myelination.